These are the notes for AP Calculus on the topic of integration by partial fractions. So before we get into integration by partial fractions, let's look at an algebra problem that's similar to what the technique for integration by partial fractions is. And that's when you're trying to add two rational expressions such as this. So in order to add them, you need a common denominator, which would be x plus 5 times x minus 2. So to get a common number, we have to multiply this fraction by x minus 2 on the denominator, and to balance it out, x minus 2 on the numerator, and we have to multiply this fraction by x plus 5 on the denominator, and to balance it out, times x plus 5 on the numerator. So let's see what that leaves us with. So if you distribute out the 3 here, that would give you 3x minus 6 over, you multiply x minus 2 times x plus 5, you get x squared. That's plus 5x minus 2x is plus 3x, and minus 10. Plus, distribute out the 4, you get 4x plus 20 over, same thing, x minus 2 times x plus 5 gives you x squared plus 3x minus 10. So now that these have a common denominator, now we can add them together. And 3x plus 4x is 7x. Negative 6 plus 20 is positive 14. Divided by x squared plus 3x minus 10. So with integration by partial fractions, we're going to be, in a sense, reversing this process. We're going to start out with an expression like this that we're trying to integrate, and then we're going to try to work back to what these original two fractions would have been. So let's take a look at the first example problem here. We're integrating x plus 4 divided by x squared plus 5x minus 6. Well, one thing you might want to think about first is another technique for integration, and why it doesn't work is if you try to just use u substitution, and in this case if you set u equal to the denominator of x squared plus 5x minus 6, take the derivative of that, which should be 2x plus 5, you can see dx would end up equaling du over 2x plus 5, which is not going to cancel out the x plus 4 there. So, u substitution in this case is not the way to go. So let's try to use integration by partial fractions. So first, if the denominator is not factored yet, let's go ahead and factor that. So we have x plus 4 divided by, if you factor x squared plus 5x minus 6, that factors into x plus 6 and x minus 1. So then what we're trying to do is take this x plus 4 over x plus 6 times x minus 1 and figure out what it would be if we broke it down into the single fractions, one having a denominator of x plus 6 plus the other one having a denominator of x minus 1. And initially we don't know what those numerators are, so we'll call that capital A and capital B. So to help us solve for A and B, so that we can break this into partial fractions, what we can do first is pretend like we're adding these together here to get this. So that means we'd have to multiply this first fraction by x minus 1 on the numerator and denominator, and this fraction by x plus 6 on the numerator and denominator. And so what that does is gives you an equation like this. So if you want to make it easier to solve this equation, to eliminate the fractions, you can multiply everything, both sides of the equation, by x plus 6 and x minus 1, wiping out all the denominators, leaving you with just the numerators of x plus 4 equals, and I'm not going to distribute out the a, it's easier to solve if you don't actually, that's x minus 1 plus b times x plus 6. Now, with one equation and three unknowns, typically that's not easy to solve, but what we can do here, based on the form of the equation, to make it easier to solve, if we want to eliminate the a's, for instance, we're actually going to let x equal a specific value, and what we can do is let x equal 1. So if we let x equal 1, then 1 would be substituted here for x, so it'd be 1 plus 4. And we substituted 1 for x here as well. And then plus b, and we substituted the 1 for x there as well. So now you do 1 plus 4 is 5, equals, that becomes 0 times a is just 0, and then it's 7b. So now we have an equation we can solve for b. We divide by 7, you see that b is 5/7. And you can use a similar technique to solve for a. If you want to eliminate the b, you would let x equal -6. So we substitute -6 for x, that would be -6 plus 4 equals a times -6 minus 1 plus b times -6 plus 6. So -6 plus 4 gives you -2. See the -6 plus 6 eliminates the b. So you just get -6 minus 1, -7 times a. And when you divide by 7, you see a, by -7, you see a equals 2/7. So now what we can do, going back to our integral, now we know what a and b are, we can split this up into two integrals. One of which would be a, which is 2/7, divided by x plus 6 times dx, plus the other integral would be b, which we figured out is 5/7, divided by x minus 1 times dx. And then in order to integrate these, we can pull out the constants of 2/7 and 5/7. The integral is a little bit simpler. And then normally what you do to integrate these is now we could use u substitution. And on this one you would say u equal to x plus 6, and on this one u equals x minus 1. But let's see a shortcut we can use on certain u substitutions where the derivative is very simple. In this case, the derivative x plus 6 du dx will just be 1. So if the derivative is just 1, then if you multiply by dx, you end up getting dx equals du. So you don't actually need u substitution at all if the derivative is 1. And that's a shortcut listed at the bottom. You can use for all integrals where this is true, but it comes in especially handy on some of these integration by partial fraction problems with time savers. So integration shortcut when using u substitution, if the derivative of u, the u dx equals 1, then u substitution is not needed in order to integrate. So what that means is we can just directly go, if du equals dx, it's not going to change anything about our integral other than the fact that this would become u. So we can just make that 2/7. And then when you integrate 1 over x plus 6, or normally it'd be 1 over u if you set it with u, that gives you the natural log. Absolute value, we don't need u substitution, you can just put in the x plus 6, since the derivative of that was just 1, plus 5/7. Same thing here, you'd say u equal to x minus 1, but the derivative of that is just 1, so we don't really need u substitution. Just write natural log absolute value of x minus 1 and then plus c. Okay, let's take a look at another example now. On this one, the denominator is already factored in factor form, so we can right away try to split this into partial fractions. Say 2 over 2x minus 1 times 3 minus x equals, one of the denominators when you split up is going to be 2x minus 1, the other one's going to be 3 minus x. Call one of these numerators a, the other one b. So what we can do first again, look at what we'd have to multiply by each of these. In order to add them together, you have to multiply this one by 3 minus x, and this fraction by 2x minus 1 on the numerator down there. So again, if we multiply both sides of the equation by 2x minus 1 times 3 minus x, that's going to eliminate all the denominators. So we'll just end up with the numerators equal each other. So 2 equals a times 3 minus x plus b times 2x minus 1. So, to make this easier to solve, we're going to have x equal, to eliminate the a's, you want x to equal 3. Notice this time it's just a 2 on the left side, so that just stays 2 equals a, and if we substitute in 3 for x, that would be 3 minus 3 plus b times 2 times 3 minus 1. So we get 2 equals, that wipes out the a's, so you get 5b. By 5, so b would equal 2/5. And then in order to eliminate the b, we have x equal, if you set this equal 2x minus 1 equals 0, you get 1/2. So it's going to make that 0. So it should equal 1/2. 2 equals a times 3 minus 1/2 plus b 2 times 1/2 minus 1. So we get 2 equals, so 3 is the same as 6 halves minus 1/2 gives you 5 halves. That's a. And 2 times 1/2 is 1 minus 1, that's 0, so that eliminates the b's. And then since we have 5 halves a, so I'll make that fraction, we'll multiply which will equal 2/5. To balance out, multiply the other side by 2/5. And that gives us a equals 4/5. So now that we know a and b, again we can split this up into 2 separate integrals. The first one would be a, which we figured out is 2/5. Divided by 2x minus 1 times dx plus b we figured out as 4/5 divided by 2x, not 2x, 3 minus x and then we can plot the constants. 2/5 on the first integral, so it's just 1 over 2x minus 1 dx plus 4/5 equal 1 over 3 minus x dx. However, slightly different than the other one at this point because that same shortcut doesn't quite work. Because here if you said u equal to 2x minus 1, the derivative of that would be 2, not 1. And here if you said u equal to 3 minus x, the derivative is negative 1, not 1. So it's just a slightly different shortcut. The bottom it says an integration shortcut. When using u substitution, if the derivative of u dx equals a constant, if you divide the integral by that constant, then u substitution is not needed in order to integrate. So what I mean by that is, notice if here we said u equal to 2x minus 1, right? Denominator, and the derivative du dx would be 2, so that would mean dx would equal du over 2. So when you substituted that in for dx, you just end up dividing by that derivative, which was 2. So let's go ahead and do that here. So that means we don't have to use u substitution here. We can just go 2/5, and we just divide by the derivative of that, which would be 1 divided by 2, so that's like times by 1/2. And then we don't need to use substitution, so then when you integrate it, it just becomes the natural log opposite value of 2x minus 1. And you can do the same thing on the other one. Plus 4/5. Here the derivative of 3 minus x would be negative 1. So times 1 over negative 1. And then when you integrate that, it would be the natural log opposite value of 3 minus x plus 3. So that gives us 4/5 times the natural log opposite value of 2x minus 1 becomes minus 4/5 times the natural log opposite value of 3 minus x plus c. So now on this one, we didn't do this on the other one, but since the constants are both 4/5, just one's positive, one's negative, what we can do is actually factor out the 4/5. And what that will leave us with is the natural log opposite value of 2x minus 1 minus the natural log opposite value of 3 minus x and plus some unknown constant. And what you can do now to make it a bit simpler is you can condense this by using the log property that when you subtract two logarithms with the same base, you can condense them into one by dividing. So that would become 4/5 times the natural log, absolute value, since they're both inside absolute value, and 2x minus 1, that would go in the numerator, divided by 3 minus x, and then plus c. So if the coefficients are the same, generally, especially in order to match up to a multiple choice problem, you'd want to condense it to make it be a little bit simpler. Notice on the previous problem, we didn't do that because the coefficients, 2/7 and 5/7, were not the same. So it tends not to simplify as much. Okay, let's take a look at one more, but this time as a definite integral from 0 to 1. So we can start off the same way. We could first, this one, the denominator is not factored, so let's go ahead and factor that. So it'd be 5x plus 8 over x plus 1, x plus 2 is what that factors into, times dx. And then, again, figure out what the partial fractions would be. So there's set 5x plus 8 over x plus 1 times x plus 2 equals to the two fractions here, one of which has a denominator of x plus 1 plus the other which has a denominator of x plus 2. Again, I'll just call these A and B. Again, in order to add these two together, you need a common number. So this one you'd have to multiply by x plus 2 of the numerator and denominator. And this one you'd multiply by x plus 1. So if you multiply both sides of the equations by the LCD, x plus 1 and x plus 2, all that's going to be left is 5x plus 8 equals A times x plus 2 plus B times x plus 1. And then it's all for A and B. First, if we want to eliminate the A's, we can let x equal -2. So it'll be 5 times -2 plus 8 equals A times -2 minus 2. Plus B times -2 plus 1. So that would give you -10 plus 8 is -2 equals -2. Oops, that's a plus 2 there, sorry. Plus 2 is going to eliminate the A's, and then -2 plus 1 is -B. So then divide by -1, so B would equal 2. get to b's, given that x equal -1, then 5 times -1 plus 8 equals a times -1 plus 2 plus b times -1 plus 1. Well, I'll give you 3 equals a 1 and the b's 1, so a equals 3. So we can split it up. The only difference now is the definite integral. So on both of them, the integrals lower and upper limits are going to be 0 to 1. And we just figure out a is 3, so that's going to be 3 over x plus 1 plus, also from 0 to 1, figure out b is 2, so 2 over x plus 2 dx. Again, we can pull out the constants of 3 and 2 there. This would be 3, let's go from 0 to 1, 1 over x plus 1 dx, plus, pull out the constant of 2, go from 0 to 1, 1 over x plus 2 dx. And then on both of these, so you'd set u equal to x plus 1 here with the derivative that's just 1. Here you'd set u equal to x plus 2. The derivative that's just 1, so we can use that shortcut. If the derivative is 1, we can just integrate without u substitution. So it'd be 3. And when you integrate that, it's going to be the natural log opposite value of x plus 1. Only thing is, if you don't use u substitution, then we're not going to convert the lower and upper limits like you normally would. So we just stay from 0 to 1 plus 2. Same thing here. So we're not going to use u substitution. The root of x plus 2 is just 1. It'll be the natural log x opposite value of x plus 2, evaluated from 0 to 1. So we have 3. When you plug in 1, that's going to be the natural log of 1 plus 1 is 2. The opposite value of 2 stays applied with 2. Minus, when you substitute in 0, that's going to be the natural log of 1. Plus 2. When you substitute in 1, you get the natural log of 3. Minus, when you substitute in 0, you get the natural log of 2. Now let's just try to simplify this further. Well, the first thing, hopefully you notice, one of these we can evaluate easily. The natural log of 1 is just 0. So that goes away. So all we're left with it is 3 times the natural log of 2. And if you distribute this 2 out, we get plus 2 natural log of 3 minus 2 natural log of 2. And notice then we've got some like terms. 3 natural log of 2 minus 2 natural log of 2 is just 1 natural log of 2 plus 2 natural log of 3. And you can condense this further again by using your log properties. You can't combine these two yet because of this 2, but remember when there's a number out in front, you can use the log property that allows us to bring that up to be an exponent. So that would make it natural log of 2 plus a natural log of 3 squared. The 3 squared is just 9, so you have natural log of 2 plus the natural log of 9. And finally, now they both have a coefficient of 1 out front, and they're both the same log with the same base of e. You can combine them into 1. This time, since they're added together, you can condense them and you multiply what's inside. So 2 times 9, 18. So that would simplify to just be the natural log of 18. And that concludes the notes for AP Calculus on the topic of integration by partial fractions.